Hi, everybody. Mr. Smith here. Today I have some bonus content for you guys. This video lesson is kind of designed for my calculus and vectors class, who are currently, for the most part, self-isolating in the midst of this pandemic. This is purely a bonus topic. It's not like necessary content for our curriculum. You can, if you feel like you want to watch the video and then just like not do anything, that's fine. Or if you want to watch the video and then look at the suggested resources at the end, that's fine too. And if you just choose not to watch the video, then that's okay too. Just post a little bonus content. But if anyone out there on the interwebs finds this video and finds it helpful and interesting too, then that's great as well. I just want to say that I am directing this kind of at the Ontario grade 12 high school student level. So some of the definitions and things I talk about might not necessarily be as rigorous as you might see in first or second university classroom. So having said all that, let's go. Today my class has been learning about the derivatives of sinusoidal functions. And a particular application that can be modeled by those kind of functions is simple harmonic motion. And the equations that govern simple harmonic motion are actually differential equations. So first of all, what is simple harmonic motion? So simple harmonic motion is oscillatory motion under a retarding force proportional to the amount of displacement from an equilibrium position. So that means in terms of an equation, so for those of you guys who, and most people who are taking this course, at least at my school, have taken some level of physics, and at the very least know that Newton's second law, force equals mass times acceleration. We know from earlier units we've done is that the acceleration is the second derivative of displacement. So any physical process where the force is proportional to the displacement can be modeled by an equation that involves the second derivative and the original function. And because they're proportional, the second derivative is some constant times the original function. So just to show you a couple examples of what that might look like, a really easy to visualize example of simple harmonic motion. Everybody can imagine a slinky, a hanging spring, or whatever. Now imagine the spring doesn't have any friction. Pull the spring down and it's going to bob up and down. And if there's no friction, if we just ignore that, it's just going to bob up and down forever. And you have this we'll call simple harmonic motion, just up and down, some period, some amplitude. For a spring, the laws governing a spring, or the law governing a spring, and this is for a frictionless ideal spring that's never going to be deformed or like stop moving. The force on the spring is equal to the magnitude is equal to some constant k times x, the deformation or the displacement of the string. So this basically means the more you stretch a spring, the more force is on the spring, and that makes a lot of sense to us. The negative here means that, if I'm pulling my spring one way, if I'm pulling the spring wants to act back the other way. And the same if I'm pushing on a spring, that spring is going to want to be pushing the other way. So it's like a restoring force. I'm going to think most that makes sense as well. It's kind of intuitive. But you can see that this equation involves the displacement x, and if since I'm just going to change to darker colored pen here just to mark this up a little bit. It's visualizing force. If you think of Newton's second law, force being equal to mass times acceleration, and acceleration is the second derivative of position, then you can see how that equation is an example of simple harmonic motion. The more you stretch, the more force there is. It's proportional. Another example of simple harmonic motion is a pendulum. And you can imagine like a grandfather clock, or lots of examples. But you pull the pendulum like a swing set at a neighborhood park. You pull the swing a little bit, and it's going to bob back and forth, back and forth. And if like nothing slowed it down, if there was no friction, it would just go back and forth and back and forth and back and forth forever. The governing equations for a pendulum we'll not dive into too much, but the restoring force for a pendulum is actually a component of the force of gravity. And the loosely speaking, the larger the angle, you can verify this yourself, between 0 and 90 degrees. As theta increases, sine theta increases well, and this restoring force mg sine theta actually gets bigger. So shown you guys a couple of very simple examples of simple harmonic motion. You might look into more complex examples like that in the first or second university course, but many physical processes can be described as simple harmonic motion. As we've seen, the equation for simple harmonic motion, the second derivative was proportional to the original function. This equation has not just a function, but it has its second derivative. It's an equation relating, in this case, the second derivative with the original function. A differential equation is such an equation involving one or more of its derivatives. If you study some physical processes later on, you might actually look at some, not simple harmonic motion, but examples where you have maybe a pendulum that's slowing down over time. And you might actually, in that case, have your differential equation might look something like the following, where you have the second derivative plus some constant times the first derivative. So something slowing down the speed of the pendulum or whatever, plus some constant, I'll call it beta, times the original function being equal to 0. And that would be a differential equation too. That relates the function with two of its higher derivatives. And frankly, most of our physical processes are modeled by differential equations. So how do we solve differential equations? We spend a lot of time in high school, in the earlier grades, learning how to solve first linear equations and quadratic equations, where we have to solve for some variable x. Well, in the differential equation, the solution is not a value of x. The solution is actually a function. So we're trying to find a function y that satisfies that differential equation. So here I've got a simple one. We're going to solve the differential equation y prime equals 2x plus 1. And in this case, one strategy we can use is something called antiderivatives. More formally, when you start taking some university courses, you might talk about integrals. In my class, the Ontario curriculum, we don't get into integration, but it is a good exercise. I give this in my class. When we first learned about derivatives, I would give my students a derivative and see if they can work backwards and find the original function, just as a good practice for knowing their derivative rules. So that's kind of what we're going to do here. We can use our knowledge of derivatives to figure out a function that actually satisfies that differential equation. So let me just mark this up here. So for our original function y, what does it have to be? Well, if we have a 2x in the derivative, that means the original function, that term would need to have a higher power of x by 1. It would have to be x squared. And as far as a constant out front, well, if I was to take the derivative of x squared, I bring down the 2, take 1 off the exponent, I actually get 2x. So that's looking good there. How do I get a 1 in the derivative? Well, that would be if I have an x in the original function, because the derivative of x is 1. That is a solution to this differential equation. However, in general, I've got nothing on the end here. In general, any constant will do. Like any function that looks like x squared plus x plus a constant c, because the derivative of c, a constant, is 0, I get that derivative of 2x plus 1. And so that is kind of a general solution to this differential equation. I could get a specific solution by adding in some restriction, such as when x equals, let's say when x equals 0, y equals 3. And so in my taking my general solution now, I know that y is equal to 3 when x is equal to 0. And then solving for this, I get that that constant is 3. So if I want this function to pass through the point 0, 3, or have a y-intercept of 3, then my function would be x squared plus x plus 3. So we have a specific solution in the case where we had some kind of initial condition, but you could also have a general solution as well. So again, not a rigorous solution there, but in general, you can solve differential equations just by using antiderivatives if you just know what the first derivative is. So that was a very kind of a simple differential equation. Let's look at another one. So in this case, I have given an initial condition here. We're going to solve the differential equation f prime x equals -1 over x squared. So if we write that as a negative x to the power of -2, that will actually make it easier for us to solve this guy using antiderivatives. This can be thought of as a polynomial. The original function, if this guy has a power of -2, the original function should have a power of x1 more than that. So x to the power of -1. And if we think about what would happen if I differentiate x to the power of -1, I'd bring down -1. That gives me my negative sign. And I take 1 off the exponent, -2. So actually, this x to the power of -1 is great. That's actually a solution. Of course, as we talked about, I can have some constant c added on to the end that would also give me the same derivative. So I might just rewrite that as 1 over x plus c. And sorry, if you hear my kids, that's my kids upstairs. They're home. We'll just deal with it. As far as what is the value of c here? So I've said that when x is 1, y is 1. So y is 1 when x is 1. We get 1 equals 1 plus c, and that means that c is equal to 0. So our solution to this differential equation is actually just f of x equals 1 over x. So again, a simple differential equation just involves the derivative of the function, and we used antiderivatives, our knowledge of derivatives, just working backwards to figure out a solution. I've got one more. In this case, I've got a differential equation where the second derivative is 9.8. The first derivative at 0 is 0, and the value of the function at 0 is 20, so like its y-intercept. We can solve this guy using antiderivatives too. So we'll start with, I'm just going to use switch to y double prime for my notation. 9.8. So using our knowledge of antiderivatives, our y prime would be 9.8 times x. Taking the derivative of that would give me 9.8, but I could have some constant, I'll call it c. Now, I've said in this question that when x is 0, y prime is 0, so I can plug that in. 0 equals 9.8 times 0 plus a constant c. So c would be equal to 0 in this case. And so my first derivative is y prime equals 9.8x. And now I can move on and find the function itself. I'll go up to the space on the right here. So knowing that, let's find y, excuse me, I'm in the original function now. Switch to pen. So what can give me a derivative of 9.8x? Well, I know I'm going to have an x squared. And then thinking of what can give me a constant of 9.8. Well, I'm going to be bringing down the 2. So whatever that is, 2 times that number has to be 9.8. So that would be 4.9. So 4.9 x squared. And that's it. But also I could get a constant. I'll add in a new constant of d. And I've said that when x is equal to 0, y is equal to 20. So 20 equals 4.9 times 0 squared plus d. Then that will just be 0. So d is equal to 20. So my function 4.9 squared, 4.9x squared plus 20. So very loosely speaking, you might recognize like 9.8 as acceleration due to gravity. I've used x instead of time, but this equation, I think I probably should have had negative 9.8. But this is kind of the math behind finding the equation of a projectile. So this might be a projectile that is accelerating downwards at with an acceleration of 9.8 meters per second from a certain height. So those were all differential equations where it was just here's the first or second derivative and use antiderivatives to find the original function. But that strategy will not work for a differential equation like our equation governing simple harmonic motion. So here's a differential equation. The second derivative is equal to the negative of the first derivative. I can use antiderivatives here to solve this one. And again, this is a function modeling simple harmonic motion. So we're kind of going to see where the periodic nature of simple harmonic motion comes from mathematically. Again, we're not being too rigorous here, but one method to find a solution or solutions to a different differential equation is to just like try out a function. So that's what we're going to do here. And actually, I'm going to try out kind of a family of functions here just for fun. We know that I might just write this up here that, if y is equal to sine x, my students have done this, that y prime, the derivative of sine x is cosine x, and then the second derivative would be the negative of sine x. So actually sine x is a solution to this differential equation. That's one solution. Another one, if I suppose dark blue is a bad choice for that section, but oh well. If y is cosine x, y prime is minus sine x, and then y double prime would be minus cosine x. So cosine x is actually a solution to this differential equation as well. We found two kind of just by inspection. Well, we can get a whole family of differential equations. If I say that I'll use f at x here, f at x is equal to some constant times sine x plus some constant times cosine x, I can actually show that this satisfies this differential equation too. The derivative of this, a is just a constant, so I have a times cosine x, and then I'll have minus b times sine x, and then the second derivative would be negative a times sine x and negative b times cosine x. If I factor out that negative 1, I get the negative of a sine x plus b cos x, which is actually the original function. So I have negative f at x, the original guy. So what I've just shown there is that any function of the form some constant times sine x plus some constant times cosine x, where a and b are just real numbers. They can be positive, they can be negative, they can be 0. So I'll just say a comma b are real numbers. is a solution to that differential equation. So I'll put a box around that. It's pretty cool. So we found that by inspection or just like trying out a function and seeing if it works. That is a valid strategy. You'll learn some higher order strategies for sure in the future if you take some more math. That's pretty neat. I have a couple exercises for you guys to try that I've just stolen from the resource that I use to teach my normal class. So just reminding you what a differential equation is. There's another differential equation. And this particular question asks you to verify if this function is a solution to the differential equation. So this is a verification question. So you can actually you have the original function, find the second derivative with respect to theta, and see if when you add that second derivative and the original, you get 0. A second exercise for you would be to see if you can reason out a function that satisfies this differential equation. The second derivative is 4 times the original function. So if you want to give those a try, pause the video, give them a try, and want to pop back in. I'm going to do these exercises as well. Yeah, pause the video, unpause it when you're ready, or just follow along with me here as well. So to do this verification, I'm just going to rewrite the original function, cos theta, and I'm going to find the first derivative. So pi is just a constant, doesn't factor into the derivative. So that is pi times cosine theta, and that'll be derivative of cosine theta is negative sine theta, so minus 2 pi times sine theta. And the second derivative will be minus pi times sine theta minus 2 pi times cosine theta. Now I've got the first derivative and the second, so I'm actually just going to excuse me, plug those in and see if it satisfies. So the second derivative, negative pi sine theta minus 2 pi cos theta. The original is pi times sine theta plus 2 pi cos theta. And you can see that, those combinations of pairs are going to add to 0. And yeah, this does equal to 0. So this function is a solution to our differential equation. So we've verified it's true. With the next one, so a function like, so again, in this one, we're determining a function. So we're not worried about finding every single one. Your function may look slightly different than mine, but if you finished it. But let's give this one a try. So a function just like sine x isn't going to work because we know that the second derivative, let's show my work here, is going to be minus sine x. And that would be true with any constant. If I had, a times sine x, from the same logic, my second derivative would just be negative a sine x. And I'm not getting 4 times. There's no way to get 4a sine x. A way to get a second derivative that's scaled higher, that's a multiple, is to introduce a constant on the x. So I don't know why I need an equal sign there. Just erase that guy. Let's try a function like this. Let's try sine of some function or some constant k times x. Let's see if we can find some values of k that actually make this work. So if y equals sine of k times x, and maybe I'll add brackets there for those who, just it doesn't matter if the brackets are there or not, just maybe make some of you more comfortable. The first derivative here would be the cosine of k times x, but here we're using the chain rule. The derivative of the inside of this function is k. And then the second derivative would be sorry, I lost my train of thought there. It would be negative sine x, or negative sine of kx, And we have through the inside is k again. So we'd actually have, sorry, I'm going to fix this up, negative k squared times sine kx. And so putting those together, we have the second derivative is negative k squared sine kx equals to sine of kx. And what we get is that negative k squared is equal to 1, kind of dividing out the sine kx from both sides, or that k squared equals negative 1. So right now, there's no real numbers that give you a value of negative 1. But one such number, if we allow to extend this into the realm of imaginary numbers, is that k is equal to the imaginary number I. This number is defined such that I squared is actually equal to negative 1. So one particular solution that could work is a function that involves imaginary numbers. Y is equal to the sine of I times x. And that's one particular solution. So a little bit above and beyond the scope of this course, but hopefully you enjoyed or got something out of that video. If you would like to learn some more, I would definitely recommend a site like Khan Academy. So I've pulled up a link here. This is the link to their section on differential equations. The language, some notation might differ a little bit from what we've talked about in class, but the general ideas are the same. And if you want to learn more about differential equations, kind of get ahead, or just for general interest sake, I definitely recommend you guys check out Khan Academy. Shameless plug there. Yeah, that's it, guys, for this little video lesson. I've included a link to the blank lesson sheet if you want to fill this in as you go in the description. Hope you guys have a great rest of the day. We'll see you online.